Okay, so the lecture today is going to be about a new set of identities that are referred to as cofunction, double angle, and half angle identities. So cofunction, of course, that refers to things such as sine and cosine, or tangent and cotangent. We had actually seen them once. We said, like, if you have two angles that are complementary, then the sine of one is equal to cosine of the other one. That idea can be expanded to incorporate a variety of other situations as well. So we are going to take a quick look at that. Double angle identities, that refers to a situation where you are dealing with, say, cosine of sum of two angles. In case those two angles turn out to be the same, like angle theta, and again the other one is also theta, well, then you are dealing with double angle, because when you add them you get 2 theta. So that's what is meant by double angle. Half angle identities in some way is directly related to that. If you can get an expression for double of an angle, you can also go in reverse and get an expression for half of an angle. So let's go through these things and write down the identities for this section. Cofunction identities, let's quickly list them. Again, this reminds us of the following. We had seen this thing a while ago, that if you have a right triangle, if you have an angle here, then the other one is called complementary. Alpha and beta are complementary angles. Meaning, when you add them, you get pi over 2 or 90 degrees. Well, if you were talking about cosine of the angle alpha, let's call this thing A, B, C. That is A over C. If you are dealing with, cosine of alpha, ratio of adjacent to hypotenuse. Let me redo this thing because my namings are. So again, cosine of alpha is the ratio of adjacent to hypotenuse, so A over C. How about sine of beta? Well, that's going to be ratio of opposite to hypotenuse, so that's going to be A over C. So you say that cosine of alpha is equal to sine of beta. In a right triangle with two acute angles, this is pretty obvious. Now, we call these cofunctions. Sine and cosine are cofunctions. Alpha and beta are complementary. So the way we phrased this thing before was that cofunctions of complementary angles are equal. Angles are equal. Well, we are going to express that fact like this. We say cosine of alpha. Well, who's beta? Beta is pi over 2 minus alpha is equal to sine of pi over 2 minus alpha. So these are complementary functions. These are, cofunctions. These are complementary angles. You can look at it from the other way around as well. Sine of alpha is equal to cosine of pi over 2 minus alpha. Or you can deal with other pairs of cofunctions such as tangent and cotangent, or secant and cosecant, and so on. Same idea applies, like tangent of alpha is cotangent of pi half minus alpha, or cotangent of alpha is tangent of pi half minus alpha, and then what else? Secant of alpha is cosecant of pi half minus alpha. It's becoming repetitive. Cosecant of alpha is secant of. Okay, we had seen all of these things in essentially the first lecture. What we are going to say right now is that these angles don't have to be acute angles. It doesn't have to be in the first quadrant. Any two angles that satisfy this property also satisfy that. Now it's possible to attack that question by drawing graphs in unit circles and doing independent cases depending on which quadrant you happen to be. That's going to actually give you a flavor of what these things are talking about. But just to give a practice on the identities that we talked about last time, let's go ahead and prove one of these things based on those identities. What are we talking about? We had that sum in difference identities. Let's pick one of them. For example, we had cosine of alpha minus beta. That was grandfather of all the identities. What was that? Cosine alpha, cosine beta, plus sine alpha, sine beta. What we are saying is that this formula can be applied to that particular case. For example, I say cosine of pi half minus alpha. I'm going to read it like this. Cosine of first times cosine of the second. Cosine of first times cosine of the second. Plus sine of the first times sine of the second. So alpha is playing the role of beta. Pi over half playing the role of alpha. Now I need to remember the sine and cosine are famous angles from first lectures. What is cosine of pi over half radians, or cosine of 90 degrees? By now we have to be very quick. Cosine of 90 degrees, that was 0. 0 cosine of alpha. What was sine of 90 degrees? You're confusing this pi over 4. This is pi over 2. Sine of 90 degrees is 1 times sine of alpha. So this is 0. This is sine of alpha. And what we ended up with is what we said pretty much first day. Cosine of complement of alpha is sine of alpha. Now, in this derivation, we don't have any restriction as to being in the first quadrant or in a right triangle or anything like that. The idea is actually applicable in a lot more general situation than this, and you are going to see quite a bit of this in elementary courses in circuit analysis. Like let's see. Not only complementary angles can be dealt with, but angles whose difference turns out to be some famous angle can be approached in the same fashion. So if I had cosine of pi 6 minus alpha, I could go ahead and say cosine of the first, cosine of the second, sine of the first, sine of the second, and the answer would be cosine of 30 degrees. What is that? Radical 3 over 2 cosine of alpha. Sine of 30 degrees is 1/2 sine of alpha. So I got something for myself. It's not as famous as the case for complementary angles, but things like these do get to be used quite a bit. In circuit analysis, you get two voltages added to each other like this, and then you want to express it as a single voltage with some phase shift in it. So it is a regular practice in some courses you are going to be taking later on. Okay, the remaining one of these angles, of these identities, I don't go through because the derivation is pretty much same as this, and we had seen all of them several weeks ago anyway. Let's go to something more interesting.
Question.
Question.
Just a second. You made a statement
Oh.
insert that value. So in the end,
You mean we are...
always use these for acute angles, but you have to.
Well, no, like suppose you take a... We said complementary angles, our new definition is that the sum is, let's go with degrees. So you say, I want to take one of these things to be 150. And you are thinking that's going to force you into supplementary stuff, which you could go that direction. You don't have to. But complementary angle of it is going to be minus 60 now. No, we don't think about those two angles as complementary angles usually because they don't show up inside of any triangle. But with our new definition, we are going to say, for example, if I have cosine of, if you want to think about it, 90 minus 60, we are stretching this thing, is same as let's see. Let's see, what is it that doesn't work here? This 150, that's minus 60. So the total is 90 degrees. And
I was just saying that you have to take the leap to an acute angle and then work the formula.
you are saying what? We have to...
When you're faced with trying to find cosine or sine and use these identities for an obtuse angle such as 150, you must make the leap to the acute angle of 30 degrees, for instance. In this case, 180 or 150. And say, okay, 30 degree acute angle, and use its value.
I'm not sure if I quite follow. Like if we want to draw a picture and follow the reasoning for it, based on a picture, yeah, you get pushed into the direction of picking acute angles and make your reasoning based on the drawing of triangles which are going to have acute angles. That's correct observation. What we are saying here, though, is that we can bypass those pictures altogether and free ourselves from being in the first quadrant and making all angles being positive in the first quadrant. The angles could be anything you want, so long as their sum turns out to be 90 degrees. When you apply the identity, that says, what did we have here? Like cosine of pi half minus alpha is equal to sine of alpha. The emphasis right now is that this alpha could be in any quadrant, you're still fine. And our identity, the way that we gave our proof, we don't have to go pick one by one each of the quadrants and check it out. So this identity is true for any angle. For any angle alpha, this is correct. It doesn't have to be acute or anything. It can be any angle. Your observation also correct that if we were going to prove this thing based on either unit circle or based on a triangle, we'll end up using reference angles, and those reference angles end up being in the first quadrant anyway. So if you have an angle here that happens to be, say, in the third quadrant, when you want to really work with it, you work with this angle. So when you want to give a geometrical proof, the the main portion of the proof relies on the properties of these angles that are seated in first quadrant. And then in those kind of a proof, you adjust the plus or minus yourself. So for example, if you are in the third quadrant, you are looking at the sine of this, you say the sine of that angle is the negative of this length. So you make adjustment yourself so that you'll be in the correct quadrant. The advantage of this one is it frees you from all those considerations at the expense of taking the flavor out of it. It's like kind of not all that clear what is going on anymore, because alpha could be all over the place and you're just used to for the first quadrant. So it's a matter of preference which direction you want to go, and the book brings this thing up here just for the purpose of saying that alpha could be any angle. And also I added this other observation that later on in many applications that the students need to understand, the problem is going to be posed in this direction. That is, this is given to you and you want to put it back into a single sine or cosine. So just keep that in mind. Now, yes?
Is that the final answer right there?
Which one?
Square root of 3 over 2 cosine x above?
Yeah, this is the final answer of this problem. Use the difference of angle identities to expand cosine of pi 6 minus alpha, and right now that's what all you want. Later on we have other things to add. Now let's go to so-called double angle identities. What is meant by this? Well, let's go review some formulas, sum of angle formulas. We have 3 of them. First one, what is cosine of alpha plus beta? Remember what that one was? Cosine alpha, cosine beta, then sine alpha, sine beta. Okay, let's start with that. Let's see where does it go. Then we have the formulas for sine and tangent, but let's not get it too crowded right now. Double angle says assume both of these things are the same. Suppose alpha and beta are the same. Their common value maybe you want to call, say, theta, so that you are not preferring one over the other. However you want to do it. Cosine of theta, and that is theta becomes 2 theta. These are same angles. Sine of theta and sine of theta. Let's write it nicer. Cosine of 2 theta. So cosine times cosine really has to be written as cosine of theta, the whole thing squared, but the way they abbreviate it, squaring goes on top of the name of the function. Same way here. So that's it. That's one of our main identities. We have cosine of twice of an angle given in terms of sine and cosine of the angle itself. Let's, for example, do a check. We say verify this for angle of 30 degrees. So what do I want to verify? What this says is that if I take this angle and double it, its cosine is same as cosine square of the original angle minus sine square of the original angle. Peculiar connection between the two. Well, let's see if this is true. This is cosine of pi third. We want to say that same as cosine square of pi 6 minus sine square of pi 6. Well, fortunately, we know all of these angles, so I can put the values and check that this is really true. Pi third. What is cosine of pi third? Cosine of pi third or cosine of 60 degrees, are we quick on that? Is just 1/2. Is that right? What is cosine of pi 6? Cosine of 30 degrees? 2. You have to square it. What is sine of 30 degrees? 1/2. We are checking to see if this is true. Let's check it out. 1/2. Is that really same as, well, radical of 3/2 squared? What is that going to be? Right? 3 over, check it again, 3 over 4 minus, what's square of that? 1/4. Why is that same as that? This is 2/4. 1/2 is 1/2. So we are vindicated on one example. For pi 6, this turned out to be true. Well, what we are saying that this is not accidental. It's not a fluky coincidence that this turned out to be same as that. What this is saying that it's always true. So one of the nice and very useful identities that get to be used over and over again. It so happens that it has 2 other reincarnations to add to our bag of stuff to carry. It gets to be used later on in 2 other formats. Those other formats come from the following. Do you remember what was the Pythagorean identity, just including cosine square of theta? Well, what was the Pythagorean identity? Cosine squared plus sine squared is 1. Now we could rearrange this in a number of ways. One of them was to say cosine square of theta is equal to 1 minus sine square of theta. By the way, on the next test, I'll be asking you of all the fundamental identities, making sure that you are up to speed with respect to them. So make sure you start practicing it. The way you practice is by reading it to yourself over and over again, writing it to yourself over and over again until it kind of settles in your mind.
You mean memorize?
Memorize. Yes. Yes. In a more politically correct way, I said memorize. So it's just that there is a trend against memorization. They say, well, this is not useful, but it actually is. If you want to advance in mathematics, memorization is essential. Consider a nurse in an operation room that the surgeon says, give me the scalpel. And he says, is that the long thingy or is that the round thingy? No, let's go, let me look at the dictionary and find out what this thing is. You want things to happen. Sometimes you cannot really wait. So memorization is important. I mean, any field, anything you do, memorization is important. So going from this course to, say, next course that you take, these things have to happen very quickly in your mind for the stuff in the next course to be possible to go through. Otherwise, it doesn't. So memorization does play a role. It's not just busy work. Anyway, cosine squared is 1 minus sine squared. And what we do is replace that with the equivalent expression. So I say cosine of 2 theta. Instead of cosine squared, I write 1 minus sine squared. Then there is another minus sine squared. So what is the net? Cosine of 2 theta is equal to 1 minus 2 sine square of theta. So, sorry. Let me see if you can do the other rephrasing as well. Somebody might say, why are you giving so much priority to sine? Why don't you give the priority to cosine? How would I rearrange this so that the priority falls on the shoulder of cosine? Of course, I start with this thing again, and this time, how do I write it? I write sine square of theta is equal to 1 minus cosine square of theta. And that is what's going to be replaced over there. So we say cosine of 2 theta is equal to, we had a cosine square minus sine square. Instead I write 1 minus cosine square. Now simplify the right hand side for me and tell me what I get. Cosine of 2 theta, then how many cosine squares would I have? 2. So let's rewrite all of these things next to each other. Make sure we see all three. Based on a case, you decide which one of them you want to use. You have cosine of 2 theta is equal to cosine square of theta minus sine square of theta. That is also equal to 1 minus 2 sine square of theta, or 2 cosine square of theta minus 1. So these are the double angle identities for cosine. And by the way, second half of this lecture would be starting from this and rearranging them slightly to get a so-called half angle identity. What does that mean? This is describing double angle instead of in terms of a single angle. If you turn it around, you can describe this theta in terms of 2 theta. And since this is half of that, essentially same identity gets to be labeled as half angle identity. Okay, now let's move on to double angle identity for sine. Well, what formula did we have for sine of alpha plus beta? Sine of alpha times cosine of beta, and then cosine of alpha times sine of beta. So one more thing to memorize. I did say that there are lots of stuff like this that needs to be memorized. So alpha and beta, let's rename both of them to be theta. Then we have sine of theta plus theta is 2 theta. Okay, I replace all of these things by theta. Let's see what happens. Sine of theta cosine theta plus cosine theta sine theta. I look at the right hand side, I see something peculiar. How can I condense the right hand side? No. What's the relationship of this term to this one? They are the same. So if you add an item to itself, it just doubles up. You have 2 of these things. 2 sine theta cosine theta. If this whole thing was an x, x plus x will be 2x. So here's my 2x. So sine of 2 theta, a little bit less crowded than that. And here is the answer. So fortunately, there's just one of these guys, as opposed to this one that had 3 versions. This is just comes with 1. Let's practice this. Verify sine of 2 theta is equal to 2 sine theta cosine theta for theta is equal to 30 degrees. So what is this asking us to check? That if that is 30 degrees, double of that is going to be 60. We want to say, is it true that this is equal to 2 sine of 30 times cosine of 30? So what are we talking about on the left hand side? This is sine of 60. Is that same as 2 sine of 30 cosine of 30? But sine of sine of 60 degrees. What was that? So where's my scalpel? Radical 3 over 2. Is that right? 2 times sine of 30. 1/2 cosine of 30. Does that check? Yes, it does. Other type of exercises like this. Suppose I ask you what is simplify cosine of 17 times sine of 17 degrees, say. That is where misunderstandings abound. In what sense? Since you kind of live and breathe with your calculators, you might just crank up your calculators, I multiply them, and I give back to the instructor. But you have to think, what would be the purpose of such a question at that stage? We are past the point of exercising our calculator. That couldn't be a calculator exercise. What is the exercise? So here to clarify, give exact value. More and more of the calculators try to defeat the purpose of the teachers, and they actually might give you exact value, I don't know. But the objective is that you refresh your mind on this. Let me see if anybody can suggest what is the exact value. You start by saying, well, if I had twice this, the identity would have told me what? That the right hand side is sine of 34. So what the problem is asking me is cosine of 17 times sine of 17 degrees. That is, well, I have to divide both sides by a factor of 2. It becomes a half of sine of 34 degrees. I'm not giving any numerical value. I'm saying that is equal to this thing. Simplify and give an exact value. So we understand that you have to rummage through your head what identity might be applicable here and use that to convert to something else. Okay. One more of these things and then we are going to take a short break. How about tangent? We didn't practice that one enough, but tangent of alpha plus beta, what was that? Over curiously enough, when you take your first physics class and they talk about if they talk about relativity there for addition of velocities, there is a formula that's very similar to this, not quite, but it's a very similar one based on so-called hyperbolic tangents. At any rate, what is the story that we are following? We are following the story, what if our angles were the same? So on the left hand side, I am left with twice that angle. On the right hand side, help me out, clean up the pieces. What's going to be left here after I replace alpha and beta with theta? Let's write it out. Tangent of theta, another tangent of theta, 1 minus tangent of theta, another tangent of theta. So, tangent of 2 theta. On the numerator, we have 2 tangent of theta. Denominator, I have 1 minus, say, 1 minus tangent square of theta. Is that right? Double angle identity for tangent. Verify the double angle formula for tangent when theta is equal to much the only one we can check. So say tangent of double of this angle, that's double of it is pi third. Is that equal to twice tangent of the angle itself over 1 minus square of the tangent? Let's see if you remember that. How can we help ourselves? This is 30, you said 2, 1 radical 3. The easiest triangle to remember to answer all things. This is 60. What is its tangent? So this is 60, or pi third. Tangent of pi third, opposite to adjacent, so that's radical 3. We are checking, is radical 3 same as twice tangent of 30? Tangent of 30 is opposite over adjacent, 1 over radical 3, or, so let's remind ourselves, tangent of 30 was opposite over adjacent. Another way of writing the same thing, radical 3 over 3, is that right? So twice radical 3 over 3. 1 minus, what is tangent square? You can take this, square it, or take that, square it. I get 1/3. So again, we are asking ourselves if this thing is true. Let's see. Twice radical 3 over 3, subtract 1 minus 1/3 and tell me what is that? 2/3. So this 2/3 and the 2/3 cancel. And we are vindicated. It is indeed same. So we checked for one case. And you will see quite a few exercises that ask you to check on these things. You want to practice those. So let's take a couple of minutes of break. If we come back, rearrange these things all over again.
Can you scroll up to the cosine?
Cosine. That's what you're asking?